Yeah, good morning, good afternoon, good evening from everywhere you're joining from. I hope you could all hear me.
Yes, we can.
All right, thank you so much. Thank you so much, everyone. It's a pleasure to be here. So, before I share my screen and begin what we have today, let me introduce myself. So, my name is Anyekan Afangide. I'm actually a computer engineering graduate from the University of Uyo. So I've been in the quantum world since 2021, 2022, and I've had some experience that was deemed fit to present it with you. I've I've applied, I've gotten the Q World, some Q Bronze, Q Silver certificate. I've also done some advanced level courses on quantum algorithms, and I've been part of one or two researches in the field. So that is a little bit about myself. I'm actually a core member. I'm in Anambra State for now. So I'm a core member actively serving. And that's a little bit about me. I enjoy computing, I enjoy anything innovation, and I believe quantum computing is the future. So here to talk about the implementation. Let me share my screen. Let me share. Okay, can you see my screen?
Yes, we can.
All right. So
But you
we
can make
will
it
be
full
talking
screen.
about. Okay, is it full screen? It's full screen.
No, you can make it full screen. That's what I mean.
Okay.
I think you should use the slideshow option. That would make it full screen.
Okay. Okay, no problem, no problem. Okay, so you can see like this. Is this okay?
Yes,
Yes.
this
Yes.
is
So
fine. But you can just click at the top left corner where you have from beginning.
yeah, that's. Is it okay? Can you see it?
Hold on, it's not sharing. Um, Go to, I think stop the slideshow on your end. Okay, now go
Okay, it
to
stopped.
setup slideshow.
Okay. It's already on the full
Okay.
screen. But- Yeah.
No. I mean, I'm trying to get you to set it up so that it will share because I think what's happening is you are seeing the full screen on your end, but we can't see it from here. So I'm trying to walk you through the process of making it so that we can see it in full screen as well. So like it's on the slideshow, and then under your options, you have a place where you are to set up slideshow. So you click on there, and then you will see browsed by an individual window. If you click on that, then share your screen again and start the slideshow from the beginning. We should be able to see you in full screen.
Okay, can you see it?
Yes.
All right. Thank you so much for that assistance, and sorry for the lag. All right. So quantum computing system design, implementation of quantum computing systems. We added in the contemporary landscape we have in the NISC era. The NISC stands for noisy intermediate scalable. What is this scalable? But it has noisy intermediate systems qubit. Let me confirm that. What that's Yeah, but it has to do with noisy. We are basically using the era of noisy qubit, noisy qubit. So our qubits are not yet wholly defined, and there's a whole lot of technicality involved in that. And um, there are some processes, some technicalities, some techniques used to achieve computability from this. So let's go and yeah, a quantum computer is simply a qubit wave function classified by or controlled by quantum or classical electronics. That is very, very important for us to start with. Because sometimes when you want to start with quantum computing, if you want to define it to someone, you begin to say, oh, we have superposition, Yeah, all of those are involved. They are part of the quantum characteristics. Any quantum system actually has it. Quantum mechanical system has those characteristics. When we talk about entanglement, we talk about interference, we talk about many more wave function collapses and all that. But basically, in computation, in quantum computing, what we do is that we are trying to control those features using classical electronics. We use classical systems such as lasers. We use pulse generators. Sometimes we generate pulses and then we input pulses into a system, a mechanism, and try to displace the qubit or the computing unit per se. Do you understand? So we basically control it with classical electronics. And classical electronics is very, very useful. In fact, most people have projected that in the hiring landscape now, if you want to be hired in quantum computing, they hire now currently more of people who are specialists in classical electronics. I mean, people who are specialists in control systems, who are specialists in cooling and material science. Like this image we have over here, this image is a quantum cryostat. A cryostat, the quantum chip is actually at the lowest point here, at the bottom here, but this cryostat is used to cool it. And you can see there's a whole lot of networking. All these wires are used for networking. There are networking cables used to communicate with the quantum chip, which is down here. Normally, this will be closed, this will be in an enclosure, and then when it's operational, it will be in milli-Kelvin temperature. It's colder than outer space. So basically, we are controlling wave functions with classical electronics, number one. Now, the wave function actually is a mathematical way of modeling, of, how would I say, of portraying a quantum mechanical system. A quantum mechanical system, a wave function is actually a mathematical way of portraying it, of writing it down, spreading of, because the quantum system we don't actually see it. These are small particles. There's a whole lot of theoretical framework, and even is going into the dimension of psychology and metaphysics of what actually goes down. Some people say that they are genuine particles, but because we can't observe them, which could actually be true, because the wavelength of light, by the time you go down to study very minute particles and you're using light to observe it, light will not be able to properly observe, tell you a picture of what's happening, because light on its own is almost bigger than, it's like you using how will I even put it? You're using a marker that is big, a chalk that is as big as this, or a pen that is big as my hand's gap now, to write on a delicate piece of paper. You won't be able to get out the features very well. So there's a whole, the best way we could describe a quantum mechanical system is using the wave function. Is using a wave function. And then in quantum computing, this is a simple wave function where we have psi. Psi is equals to alpha. Alpha is a probability distribution of the zero state plus the beta. The beta is also the probability distribution of the one state, meaning that the state psi is in the state, is in a probability of 0 and 1. I know we are all conversant with that by now. So we use quantum computing. We try to emulate nature in computing. We try to emulate nature. There was a time I was giving this talk sometime in my office space, and then while writing, while preparing, I spent half the time, spent over 2 hours trying to define what computing is. What does it mean to compute? If you say you compute something, what does it mean? So I thought really deeply, and there was no one solution actually. But computation, if you remember when computation is simply trying to take a measurement from the system and then act upon that measurement. You take a measurement from the real world and act upon that measurement. That is a layman. I'm just in my own understanding, in a way of breaking it down. So when we use quantum computation, we are trying to, of course, you could use classical, you could drop bottles and then use them to count, do arithmetic, addition, subtraction. But there are some level of computations that are so complex that the only ways we could do it is to consult nature itself. Is to consult nature itself. Because why do we consult nature? Because nature actually does the computations. I mean, if light, incidentally, light hits on a particle, there's a distribution of energy that is characterized, is described by Einstein's equation, Einstein's photoelectric equation. So use the quantum method, the quantum that will be able to carry out some intractable calculations with more efficiency. That's the entire essence of this. So we are going to look at this paper is basically going to cover, this presentation will cover me trying to briefly describe some methods which we have. There's no one modality, there's no one way we represent quantum systems in computation. There's no one method. There are several of them. So I'm trying to introduce and then show us the working principles behind some of them. So that is basically what this is going to be about. So let's start with the quantum bit. The quantum bit is the essence of what we are doing here, the qubit, because a collection of qubits together that are entangled, that is a simple quantum system. That's a quantum computer. A collection of qubits that are entangled is a quantum. You know, I was in my PPA, I serve in a university. So I went to meet this lecturer, this prof, and then he told me that they have done a research. He's actually in the physics department. Someone did the research on nanoparticles, and then in the abstract, just a one-line statement, the person wrote that these particles could be used to implement quantum computers. And what are those particles? Those particles were actually, they were kind of ions. They were ionic molecules or ions per se. So those ions, if you isolate them, they have quantum properties. And we should be able theoretically now to, the same way I said, use classical devices to work on them, to manipulate them, to be able to carry out computation. So you see, that in an essence, we have created a quantum system. It's now an engineering problem, looking at, okay, how would you be able to talk to this ion? How will you be able to talk to this qubit? How will you be able to put it in entanglement? Okay, you've been able to have it in entanglement. How are you sure? To what degree of accuracy are you sure that this thing can represent or can hold a state? Do you understand? So a qubit can represent, a qubit actually is any system, quantum now, we are looking at quantum system, that can represent data. You have to have distinct states, a zero state and a one state, a zero state and a one state, a zero state and a one state, or a superposition of both of them. So this is actually a qubit. Oh, sorry, I skipped that. This is actually the representation of a qubit. And I actually use, there's this free tool that is available via GitHub that you can use to generate at least most quantum states, that is qubit states. So if you click on this link, I'll share this later on. It will take you to this GitHub page where you could freely just move it around, wobble the qubit around, and then test some of these states and also see their corresponding wave function. It's actually a complex wave function. Now, this on its own, if you're tempted to look at it, that a qubit could go in any state on this sphere, but there are still some states we can't see here visibly, because a true quantum state can actually or naturally has a complex domain to it. So there are some of the states you can't visibly see here. But right, what I'm trying to say is that the Hilbert space of a qubit is far larger than what we could comprehend. It contains even the imaginary, the complex aspects of that space. What that does, that we are trying to, whenever you have a qubit system, you just isolate a one state and a zero state. You isolate two states that you use as your fundamental basis, because stemming from classical computing, now we have classical computing actually has it's just like a switch, a zero or a one, but a qubit should have a zero and a one, and also a complex superposition of both of them. That is what a qubit is. So it has these properties: superposition, entanglement, and interference. We'll look at them in a bit. Let's go. So superposition is simply just the ability of a qubit to be in a linear combination of multiple states at once. It could be here in a zero state. This is the first one in a zero state. It could be in a one state. It could be in a one state. The zero state is what we call the ket zero. The ket zero is actually a vector state. If a vector, you draw a vector, a linear vector, 0, 1, and 0. It stands for the zero state. Then this one state, the ket 1, is actually another vector state, 0 on top and 1 below. That gives you your one state. Or it could be in a complex or a superposition of both of them. Now, this is the fundamental superposition state. It's actually a Hadamard. A Hadamard is a gate that actually puts a qubit in superposition. So the Hadamard, when you're in zero state, the Hadamard flips it to the plus state. If you see, this is just half of this sphere, and the plus state actually, these are the probability amplitude 1 over root 2. They are normalized. They are normalized, meaning that if you square the probability amplitude, the sum of the square of probability amplitude should be equal to 1. Now, that means out of the entire Hilbert space, out of the entire space, we are only shrinking it down to 0 and 1. It's a normalized state. It's a normalized state. So within the scope of this talk, we'll be dealing with this normalized state. So entanglement is simply, please, wherever you have a question, wherever you have a contribution or an opinion, you can feel free to let me know. So entanglement is a unique quantum phenomenon too, where two states, this is a graphical illustration, so it's not always like this. It's not always, in fact, there's a paper I read while coming up with this. It showed that two photonic qubits were entangled over the distance of 230 meters, probably in a campus area, maybe in two different labs. They were entangled. And how were they entangled? I think they connected a fiber link, a fiber optic cable between both of them. And then when a reading comes from one, it automatically is detected on the other one as a counter of what the other one sent. So they were entangled, they were in a state of entanglement. Entanglement simply means these two qubits are correlated. These two particles are correlated. A simple example of entanglement, this is an entangled pair of two electrons. We could see, not two electrons, two qubits. We could see there are two qubits because we have two states on one part, two states on one part, two states on this part. So if you look at this thing very critically, I'm not with a whiteboard here, you see that it is not possible. You cannot factor them out. You cannot say you take out, normally a quantum state, you could actually factor it, but you can't factor, if you take 0 out from both parts, it doesn't really work. If you want to say you take 1 out, you take 1 out from this side, but it doesn't really work. So you can't decompose it to simpler elements. They are entangled. They are entangled. Entanglement now in a physical qubit, since we are talking on implementation, a physical qubit, we could say, how do I put it? Like I read one paper by Zanadu. Zanadu uses photonic qubits. They use light for qubits. They join two photons together, and in an enclosed space, those two photons, there's a readout. There's one readout. Just imagine a space where two photons come together, and then those two photons they interact. You don't really know how they interact, but one readout is gotten. Now that one readout, because when a photon interacts on a particular matter, a piece of an electron, whatever it is, it energizes that item, that particle. So when two photons now are interacted together, the result that is read out is an entangled state. Is an entangled state because you can't actually decompose that output and say, oh, this output came from maybe 50% from A or 50%. No, it doesn't really work like that. It's an entangled state. So, in essence, when you want to create, as I said, there's no one-way solution. If you want to create an entangled state with optical qubits, you could just put those photons together, and then they come out entangled to each other. So this is just an artistic representation of entanglement between atoms. Entanglement can occur between photons, atoms, ions, and so on, energy levels, so on and so forth. So interference is another property of qubits, of quantum bits. where one or two qubits, because of their wave function, they interact together either constructively or destructively. A very famous example is our double slit experiment. This is a double slit experiment where an electron is passed, the electrons are to be photons or particles. They pass through a slit. This can actually occur in the macro, in the real world. If you try and get a box with two slits and you allow sunlight to come in to permeate through those two slits, and then inside the stack, you will see an interference pattern, meaning that the light that is coming, the light is not just quantized as Einstein proved, but the light actually inherently comes in form of a wave and a particle at both instances. So it forms an interference pattern, and this is actually two or more qubits, two or more quantum states, two or more quantum objects. Whenever they just relate with each other, even if they are not entangled, whenever they relate with each other, there is an interference that is a combination of their wave function. It combines and then spreads out different probabilities. Like now in this output, this interference pattern, if this was a probability distribution, you see that there's a higher probability for the photons to appear here. They are now reduced and more reduced probabilities for them to appear on either side. Yeah, so that is just the fundamentals of qubit. So now you have your qubit, or we have basically seen the the probabilities, the not probabilities, the characteristics of qubit, the fundamental characteristics of qubit. Now you want to use those qubits to create a quantum system, to create a quantum computer with usable quantum properties. We use what we call the Vincenzo's criterion. Excuse me. So what this means is that it was actually postulated by this guy, Vincenzo. So the Vincenzo, I think in the year 2000 or 2001. I'll try and list that paper. I don't think I listed it here. But basically, there are five criteria that he listed for you to be able to use qubit. I said qubits are the fundamental building blocks of quantum computers. In fact, if you could have standalone qubits that carry out all these criteria by themselves, that is a quantum computer. The remaining things are just input, output, and control. Input, output, and control. So for you to be able to work to make, usable quantum computers, use this criteria. Number one, you should be able to initialize the state of the qubit to a simple fiducial state. This fiducial state is like, as I said earlier, you're able to instantiate it to be either a zero or a one. That is to make a basis. You make a basis. Your basis, please take note, when you're dealing with qubits, we are going to see some examples of quantum system. It's not that in classical computers, in classical systems, we have, when you want to deal with transistors, some transistors, they have an on state where you have 5 volts, an off state to be zero, or so on, depending on the, maybe even your processor. Your processor has billions of transistors. The voltage levels will be very minute there. I can't really state them now, but they'll be very minute. Then they will function as on and off state, zero or one. But in a quantum state, a quantum system, what you simply do is that you highlight a state. Maybe let's assume you're using a neutral atom. Maybe this atom, you know atoms now, atoms have electrons, that those electrons, they exist on discrete energy levels, on energy levels that are discretized. So imagine you have the normal atom is neutral, and the outermost electron, maybe a Rydberg atom, it stays on one energy level n. And then when it is excited by maybe an output, that energy level n increases to energy level n plus 1. You could use those two states as your fiducial state, as your fundamental state. You could use them as your basic state, but you will not just write it, you just write the wave function equivalent of them. That means if it is on energy level 0, it is on. It is on energy level 1. So you just get those and then you use them as your basic state. And every other thing, we have dealt with quantum gates. The last speaker spoke about we're trying to instantiate some qubits, we're running Hadamard and some other gates on them. So imagine you have those two gates, those two states rather, that is existing in 0 and 1, that are represented in real life by the energy level of the outermost layer of an electron of an atom. So you just have to map it. It's not a mapping problem. You map your one state to probably the energized state of the atom. You map your 0 state to the normal level of the atom. That's in atoms. There's an implementation called cold atoms. Not cold atoms, they call them, or neutral atoms. Yes, neutral or cold atoms. They are ground state. They don't really interact. So that is the first criteria by Vincenzo. The second criteria is that this state or this qubit you want to use, you should be able, they should be able to function as, you should be able to have a set of universal gates amongst them. You should be able to have a set of universal gates amongst them. What does universal gate mean? Universal gates, like in classical computation, they are a set of gates with which you could use them to perform a whole host of other gates. You can use these basic gates to be able to perform a whole host of other gates. I wrote a few of them now. You have like your rotational operators, or your rotational, like this parameterized gates we use. So those parameterized gates, they are rotational, the ones we use, because their Ry rotates in the y-axis, Rx rotates in the x or z axis. So your rotational gates are part of the universal gates. You have your Clifford gates. Clifford gates too are very useful. Clifford gates are examples. You have your Hadamard, your C note. Those are examples of Clifford gates. And then you should also have uh, your Toffoli gates. That is a controlled NOT gate. Controlled NOT. CC NOT gate. A CC NOT gate can actually be used to implement all other Boolean operators. So if you want to have a Boolean function, maybe Boolean dealing with yes or no, true or false values, your Toffoli gate, which is a CC NOT gate, could be used to implement those. Now, this next criteria, the third one, a qubit should have a specific measurement capability, meaning that whatever you use as your qubit, you should always have a means to get output for it. It should not be okay that you should be able to initialize it. Most qubits are initialized by lasers or microwave pulses, whatever the case may be. You should also have a way of reading from it. Do you understand? You should be able to read. When you perform the measurement gate on Qiskit, when you do like maybe Q dot measure, as you're measuring the gate in a quantum circuit, QC dot measure, you're trying to, that's what you do on the abstraction level, the programmable, the software level, but on the hardware basis, there should be a way to read out the output. Now it should be scalable. The fourth one, it should be scalable. A scalable physical system, you should be able to scale it with well characterized qubits. Your qubits should be characterized. You should be able to characterize them. Individual qubits. We are going to see some in superconducting qubits. You see that in a superconducting qubit chip, you'll be able to sort out 1, 2, 3, 4, 5 qubits well characterized. You understand? And then the final one is long coherence times. Long coherence time. You know, a quantum state inherently is susceptible to noise. Is susceptible to interacting with neighboring particles, neighboring states, neighboring wave functions, because these things are very minute. So they are very fragile, as I would put it as that. So what happens? Coherence time is the amount of time that this thing has a high fidelity, that has a high probability of being usable, meaning that if you keep just the way we initialize some qubits on Qiskit, and then you put in, maybe you use an X to initialize it to a 1 state from a 0 to a 1. How long on a physical qubit, how long are you sure that this thing will remain on a 1 state? Some have coherence times of up to days. There are very few implementations that don't quote me. There are very few, especially trapped ions. Trapped ions have the longest coherence times, whereas some other implementations, the coherence times are very, very short, very, very short. So these are the Vincenzo's criteria. They are actually seven. The remainder two for actually programming in programming when you start dealing with programming and implementation of these qubits. But these are the basic ones to build the qubit, which is what we are considering now. So these are some qubit modalities I'll be talking about: superconducting qubit, trapped ion qubit, photonic qubit, neutral atom qubit, quantum dots, and diamond center qubit. We are talking. I'm going to pay more attention on the first three because if we were to go dive into all of them, there's a whole lot. There's a whole lot. There are even more being postulated on a daily basis. There are even more. Like in my PPA now, we're actually trying to implement one using spin. I know spin could be categorized under one of these, but basically, let's see what we could do with some of this. So how do we implement this qubit? Let's look at the first one, a superconducting qubit. This is one of the most popular qubit implementation. It's used by IBM, it's used by many other providers, and it basically uses a superconducting chip. So what you're doing is that it's actually like a capacitor. There are two capacitors, there are two superconductors that are linked together. They don't really touch, so they form a kind of capacitance. And then because of that, they are allowed some kind of Cooper pairs. That means there's some interference between both of them. They call them Cooper pairs or Cooper pairs. That means superconducting electrons. They tunnel through the barrier because you don't really join both of them. This is an example of them, but this one is called the transmon qubit. This is an implementation still of a superconducting qubit. So a superconducting qubit, information is stored in degrees of freedom of nano-fabricated anharmonic. It must be anharmonic. I'll show you why. It must be anharmonic oscillators constructed by a superconducting circuit element. In a superconducting circuit, you actually have a supercurrent that flows, and you'll be able to have a whole lot of quantum properties that will spring up, that will pop up. So this is actually based on, for those of us who did physics, of your LC resonance circuit. On an ideal LC resonance circuit, you have a harmonic oscillator. That is where an harmonic oscillator. That is where it comes out. But because we use these superconducting qubits and we are able to postulate them, we are able to implement them so that we get an anharmonic. This anharmonic oscillator is so that we actually have two distinct energy levels that will be categorized as your 0 or 1 state. So this is just an example of the picture here we have on our right is actually a 4-qubit system. These are 4 qubits. These are transmon qubit, and you see here you have their measurement readout mechanism. You see this whole bus is reading out each of them. These are the qubits. You read it out. See, you must have a mechanism for reading out, and then this here you see the buses, all those lines in between. Those are the buses, the connection wires where you supply your microwave pulses or some other pulses. You need to pulsate them to initialize the gate. So basically, what happens is that you make use of a Josephson junction. The Josephson junction, what I was explaining with superconducting materials, is actually called a Josephson junction, and it forms a capacitance, a capacitor, a Josephson junction capacitor, or you use transmons. These are the case of transmons. These are the case of transmons. Transmons, the basic difference between transmons and Josephson junctions is that transmons, they actually have a superconducting element, charge element that is put, an extra capacitance element that is put in the circuit. So it has actually lower activation energies. That's lower and it is useful for that. So that's the difference between Josephson junctions and transmon qubit. So when you have your Cooper pairs, that is when the capacitance between. So basically, what we are measuring in a superconducting qubit, in essence, when you break it down, is actually capacitance. We are measuring the capacitance. the energy level of the capacitance, which we call the Cooper pairs. That's what we actually measure in superconducting qubits. And because these things in the name, as the name implies, superconducting qubits, for something to be a superconductor, they have to be cooled down to a very low temperature. So these are usually in large dilution refrigerators. They store them there so that they could have these properties. If they are not stored there, heat will just immediately. Of course, these are initialized with microwave pulses. Microwave provides some kind of heat. It provides some kind of heat. So any external heat from the surrounding, it functions as noise and it will decohere this system. So it must be kept very, very cold. So this is again, this is your measurement. This is the qubit itself. This is your three. Is it forming a kind of capacitance, a transmor qubit? You have your buses that take out input and output and your measurement. So clear? We are still all learning this. We are still learning this, but this is basically how it works. So that we'll be able to see quantum computing as not just an abstraction, but we'll be able to see it for what it is. We are trying to implement nature. In this one, we are implementing the energy levels between two superconducting materials, the capacitance. Now, this is an illustration of, oh, sorry, this is an illustration of the energy
Sorry,
level.
sorry. Before
Sorry,
you leave
come in.
that, yes. When you were talking about energy level, I wanted to see clearly from this circuit diagram. I want to see something that makes us see clearly, because I'm from a mathematics background. So, I mean, coming to learn engineering from you will be a great one. So, the energy level here would be between the
Absolutely.
there are four qubits here. I see between the qubits,
Yes.
or on one qubit, there is energy level. How do you translate that?
Okay. Sorry. So as I said, the superconducting qubit actually for it the name is we term it superconducting qubit. But to implement it, we use what we call a Josephson junction. A Josephson junction is a capacitor in its essence. I'm stripping down a whole lot of abstraction. It is actually a kind of capacitor. You understand? And you know a capacitor holds charge. So in this qubit now, you see four qubits. This qubit actually, this first one here that you see, I don't know if you could see my mouse, is actually a kind of capacitor, and there's charge, is a capacitor holds charge. So I would suggest to me that it is actually the abstraction between a full charge and a high charge, or maybe two distinct energy levels within each qubit. But these wires, these buses you are seeing now, these buses are actually, if you look at them closely, they are connected to all of the capacitors. This is a simple 4 qubit system. They are connected to all of them, and they can be used for entanglement. Where this one, the energy here can actually, based on your input, communicate with another one, thereby um, implementing that those quantum features, those quantum characteristics, entanglement that we spoke of. So these buses, if you notice very well, these buses are connected between all of them. So this is just a 4 qubit system. And then we are hearing IBM saying they have, I think the highest now, it should be the Heron. Please correct me if I'm wrong. The Heron chip, or is it the Eagle or the Heron? It has almost 400 qubits. So when you have 400 qubits, each of them almost similar like this, you have a major problem in terms of communicating. That's why the last speaker, he spoke something about transpiling. Transpiling is very important because the way these qubits might be connected, you want to, maybe you initialize 10 qubits and you want to run a control NOT gate and a Hadamard gate. That is actually an entanglement. When you do a Hadamard and a control NOT, you are entangling those two pairs of qubits. So you want to run them within 2 qubits, but you don't know that those 2 qubits are located, the topography, the topology is the word. The topology are very far apart on top of the qubit system per se. So there's a whole lot of mapping that needs to be done, and transpiling. Your simple code on Qiskit needs to be transpiled to properly suit this system. Not only because of the topology, but because, how will I put it? What I'm trying to say now, I did not cover it here, is actually further. The way the way this system, let me put it, the way this system would represent a state, it might not be in the normal, it might not be the normal X gate where you're fluctuating from X and X gate from 0 to 1. It might not actually be so. It might only be limited. Remember, I said in a true quantum qubit, it has a unlimited. I don't know, those of us that are physicists here, I'm not a physicist, I'm still learning this, but a truly, they call it a Hilbert space. A Hilbert space is like the truly unlimited space of possibilities, and they cover the complex domain and the physical domain that a true qubit should be able to represent is actually very unlimited. But this physical qubit now might, in theory, might be only able to move in, let's say, 2, 3, or 4. It can be able to move only 2, 3, 4, let me call it positions, that it cannot go to that unlimited number of states. So what happens is that when you put a Z gate, or maybe an X gate or a Hadamard, maybe the qubit, I don't know, it depends on the hardware per se. Maybe the qubit might not on its own be able to flip to a Hadamard gate, but because remember we spoke of universal gates, some of these complex gates can be built from fundamental ones. So what happens is that the circuit, the code, the compiler transpiles what you are inputting on the Qiskit interface, transpiles it to a form that this qubit will understand. Maybe this qubit, let's assume this qubit can only move in C naught, CZ gate, and maybe CCX gate, that is a Truffle gate. A Truffle gate can only move in, let's assume. So when you put your X gate, how will you move in the X gate? It will not be able to move in the X gate. But what happens is that your code transpiles it to suit here. That is actually what I wanted to say. That I'm just shedding more light on this, so that we appreciate what is actually going on with IBM. IBM are doing a lot. And not one person can know all of these things. It's actually hidden, it's abstracted beyond your view, even beyond my view. Probably you need to work there to know exactly how these things are implemented. But what I'm trying to say is that the topology also matters. So what I'm saying is that there's a capacitance here and there's an energy level that is shown in this next diagram here. This diagram shows the energy level of a transmon qubit. So this is your normal LC oscillator, your LC circuit. You did physics. L stands for is actually the inductance, the capacitance. If charge is stored in the capacitor, they just keep on moving. The capacitor gives charge back to the inductor. The inductor charges the capacitor back. The inductor capacitor, it goes on till infinity in an ideal system, But basically what we do here is that since it's anharmonic in this case, the current will be, the charge will be dropping from time to time. And with these our transmon qubits here, you see that only the first two states, I can't see mine, the first two states are distinct. The first two states are, would I call it, they are big enough. You could actually identify them. You could, as in a transmon qubit, since it's anharmonic, the energy levels tend to drop more and more and more and more till infinity. So you are just working with these first two. These first two are distinct. You could now give it a state as your 0 and 1 state. C'est clear? So you now have your 0 and 1 states now in your transmon qubit. And with that, the transmon is the one by your right. And with that, you'll be able to now these other ones can function as probably a superposition of both of them. I'm not really sure, depending on the implementation. So you see, this is your computational subspace, this 0 and 1 state, because they are the most distinct. The other ones will be phased out till infinity. So that is my little contribution to superconducting qubits, which is what IBM uses, which is what Qiskit uses. So clear? Is that okay? All right, let me go to the next one. Trapped ion qubit. Before I started serious research, I was a pessimist. Should I call it? I was a pessimist of um, of superconducting qubits. I mean, optimist rather, not pessimist. Optimist. I was optimistic about superconducting qubits because it's what IBM used, and I was introduced to quantum computing on IBM's devices. I used IBM's Qiskit. So, but later, somebody say later, as a preacher would say, later I now got to know that trapped ions, they actually hold a whole lot of prospects. Trapped ions, number one, they hold the longest coherence time. They have the longest coherence time. And if you follow the ecosystem of late, this company that released this particular qubit is called IonQ. They went public some months back, and aside from that, they were able to implement quantum computationality. I don't know if that will exist, but they were able to using their qubits, their systems, they were able to try say carry out a quantum computation to the order that no, they call it, is it AR or AU, AR64, meaning it's actually 2 raised to the power 64, which is about 16 quintillionth number of operations per second. It was a breakthrough. IBM has not gone, nobody has gone so far on a quantum device, even in classical. For a quantum device to be able to do that is, and I'm sorry I might be sounding biased. I know this is sponsored by IBM, but I'm just stating the facts. So trapped ion qubits, basically what happens in superconducting qubits. Let me say, what we did previously, we are trying to simulate the energy of an ion. So we could, they call it artificial ions. The the whole name of that is, they call them artificial ions basically. But these ones they call these ones what do they call this one? They call them natural, or could I call them artificial? Okay, they call these ones artificial atoms. Okay, those are artificial atoms. These ones are now your normal, they are true ions, they are true trapped ions, as the name implies, trapped ions. So superconducting qubits are called artificial atoms. These are true atoms. So basically what happens is they deal with an atom. You know, when you knock off one electron or you add one electron to an atom, it becomes an ion, becomes ionic. Now, when something is ionic in that nature or in that size, that minute particulate size, it has quantum properties. So they trap the ions, or ion as the case may be. They trap them using all these you're seeing by the side are just input or output. Remember the Vincenzo's criteria, they are used to either supply a voltage, either supply a microwave um, pulse, or some other pulses to it, and they are able to instantiate the the atom. But the atom can remain here for a longer time. Look at here, ions can be confined for weeks on trapped ions, but it can just be confined individually. Another important thing to know when dealing with quantum systems, that have when we are trying to when we are trying to instantiate quantum systems on the quantum level, it's one thing to prepare a state, it's another thing to keep that state for a long period. So one qubit, single qubit operations are relatively easy to do. Single qubit operations are relatively easy to do. But by the time you start coming to multiple qubit operations, 2, 3, 4 qubit operations, those control operations, you are spreading your wings across several qubits. And if you remember the way the qubits are laid out from our previous example, you see that it's actually an engineering challenge. So those multiple qubit operators, they have lower fidelity. If a single qubit should have a 99.9% fidelity, that is the gate, a single qubit operator, like a Hadamard operator on only one gate, one qubit. An X gate, a Y gate, is only one qubit. But now, by the time you have a controlled X, a controlled Y, a Hadamard or a CEC X gate, you're dealing with multiple qubits. And for some implementations of quantum computing, you can't even do that because it's virtually impossible to hold multiple qubits to be coherent, to even carry out computation on it. So that is one of the things we need to keep in mind while we are trying to produce um, your quantum states, especially multi-qubit gates. So what I'm saying is that you trap ions here, and those ions they interact with each other. They interact with each other. They use actually, since we are using the physical states of the atom. Let's say you have a Rieberg atom. A Rieberg atom is just, or ion is simply an ion or an atom that the energy level has simply been exaggerated. Maybe you excite this atom so much. Imagine an atom that has two shells normally, and then you excite the last or the valence electron to a very high energy level, giving it theoretical properties of that atom. So it is now taking the property of an atom that is way, way bigger than it. We call those Rydberg atoms, and they are mostly used here too. So single ion qubits can be confined in traps for weeks or longer. So you could confine a state for a week or longer, and initialization is possible through laser manipulation. You could use laser manipulation, or you could use other. By the time you pulse a laser on those atoms, you send the laser. The laser, laser are photons basically. The photon will excite or interact with the atom, and then there will be either an energy loss or an energy gain. Remember quantum electrodynamics. That is actually the theory, the framework that actually deals with operation of things in the quantum world, quantum cavity or quantum electrodynamics. So electrons or photons use part of their energy to electrons or to atoms or to ions, as the case may be. And with that plus or minus, you see, you can now start building computation. Remember, I started with what is computation. This is, you are just able to excite the atoms, get them to Nobel state, make them to interact, entangle with each other, and with that, you are able to carry out computation. So is that okay? Is that okay? Please excuse me. Let me go somewhere where I have
Yes, we are with
my
you. We are with
yeah.
you. We are with you.
All right. All right. Thank you so much, sir. Sorry, let me plug my system. Now, the next state we have photonic qubits. Photonic qubits are another implementation of quantum computing. And simply put, these ones they make use of photons to carry out computation. We are still coming at this keyword computation. In fact, one class, I organize a class, we sit down and define what computation is. Because if we know what computation is, we know that quantum computation is just a type of computation. There might be more, who knows? I'm just postulating, I'm being as on the lighter note. So we use qubits, photons to generate qubits. A photon on its own can be seen if you're able to isolate it properly. You could use it to form a qubit. It's a quantum system. They say that photons are, when I was researching for this, photons are they are one of the easiest quantum objects we have, photons. Of course, they are tiny, they could tunnel, yes, and they could exhibit quantum properties. They could interfere. They are entangled. So why couldn't we use them? So some people use photons. A company that uses photons is they call it Xanadu. Yeah, Xanadu. Xanadu use photons and um, AI. They are known for photons and AI. So basically, this image you're seeing is an example of, it's just proving the quantum property of a photon. They are proving the quantum property of the photon. So you see a laser, it's called the Mach Zehnder, is an interferometer. Interferometer meaning to infer where actually the qubit or the photon is at a particular point. So what it simply does, a qubit, a photon leaves. This is just to illustrate how a photonic qubit works. It's not to say this is a photonic quantum computer implementation. But we should have this in our physics labs, of course. So a laser, if a laser comes to this beam splitter, it is actually splitted. It's actually splitted, which gives the property of uh, not entanglement. You're putting it in a superposition rather. Yeah. So the photon comes, and then automatically at this point it has, sorry I not put the probability amplitudes or the probabilities here, but there's a 50% probability it goes here, 50% probability it comes here, just by passing through this beam splitter, and then coming here it hits this mirror, these are separate parts. These are separate parts now, and then they come now with another beam splitter, and then they are joined back together, and then they land on this photographic film. If this was a real apparatus, you could measure, and then you see that the phase remains the same. The phase of the light, we all know light moves in separate phases. The phases remain the same. So this is an example of, you could see here, this is your superposition, your superimpose, your superposition, you're putting this super, and then this part, everybody you could see them. They might be entangled to some degree, who knows? They might be entangled based on the phase you put through, and then they come back. And if you notice, this beam splitter is in the same phase. You might see this direction, but it means it's in the same phase. So it joins it back together. That's simply what will happen if you use qubits. If you perform a Hadamard 2 times, I'm right? If you perform a Hadamard operator 2 times, a Hadamard on state 0 to give you the plus state, a Hadamard on the plus state to give you back the 0 state. So this shows that you're a photonic. So yeah, and they have an advantage of photonic optical qubits is that you could operate them at room temperature. So all other qubits, ionic qubits, ion trapped, superconducting, they need literally to be very cold environment, very cool environment, so that they will not take noise. But a natural property of photons, thank God, is that they don't interact, at least physically, they don't interact with heat. So we could use this in a this could be used without need for cooling. In fact, photonic qubits they are the ones that are most easily used for, should I say, proof of concept. If you go to most labs in foreign countries, foreign clients, they have this apparatus set up. They have simple 1, 2, 3 qubits or 2 photonic qubit system set up, because they don't need to spend much money for cooling. Cooling actually takes a whole lot of money. I mean, to set up one of those cryogenic things you see there, you need liquid helium. I think liquid helium. So you need to be passing liquid helium.
Hmm.
It cools that those things back then. But with this, you don't need all of that. Example of the photonic setup, the photonic quantum computing setup in a lab. So they just pass a laser through a whole lot of lenses, through a whole lot of mirrors, beam splitters, and then you are able to get output. You are able to carry out a fundamental, maybe quantum reading or change of state. So this is how it is in the lab, in a lab environment. Of course, you can see the close. This is a lab. So I don't need to tap on this.
Sorry,
This is a lab.
before you leave there,
Yeah.
yes. Yeah, just to have some clarity in what you are saying. In the last diagram, where the laser is passed through the beam splitter 1 and 2. Now, from that picture, I just need to get something clear from you. On the screen, are we saying whatever goes through, we get the complete thing outside on the screen? Let me also say this. I know that, like you said, this beam splitter is used majorly in quantum optics. I've read things on
Yeah.
materials about it. I mean, where they show the mathematical and physics tools, they go to the lab and experiment, and these things are true. But from this diagram, I just want to get it clear that the laser supplied, I mean, that splits, then goes back to the screen. Does we get all the results back?
Okay. Now, the fundamental, now we come again. The computational element, what we are computing in the laser, it's not just the laser, it's the photons, the lights, the photons moving through. And then the quantum property of a photon, I don't know if anybody can help me with that. Quantum property of a photon is the phase, it's usually the phase. Sometimes, so we are observing the phase of this light. There's this experiment where they pass light through some kind of lenses that have different phases, and you see that when sometimes they are superimposed against a negative, when they are counter the phase of the light, it blocks the light, but when he allows it in the phase, light flows through. So what we are observing is the phase. So this thing comes and then it distributes the light with equal probability here, but it's the phase we're actually looking at, and it joins it back because it's the same phase. So this distribution, this superposition now is this superposition is based on superposing based on from the phase. So if we have a Hamiltonian of the phase, you see that at this point where the superposition occurs, and here at the end is the same.
Thank you.
Please feel free to correct me if there's anybody having a little addition too, because we, one man cannot know all of these things. We are still learning. Now, this second one is, as I said, this is the implementation of an optical setup in a lab. This is a lab. They are doing a whole lot. And another important thing about optical setups is you could, light can pass, light can carry so many packets of data. There'll be so many photons at a time. I'm just saying that. So on the engineering perspective, from the engineering perspective, you should actually be able to compute very many qubits through just one, that is pass them, multiplex them through just one laser pulse. You multiplex, you bring them together and send them as one. Now this is an example of a chip here. This is an example of a chip by Xanadu. So this is a nano photonic chip. So this chip, meaning that it is small, it is not as big as these setups here. It is a small chip, but light is being fed in through this. You see, this is the waveform here. Light is being fed in with specific waveforms, and then computation occurs. This is entanglement. You hit two of them together, you entangle them, and then you carry out computation. This is hard coded, as I said. Remember when we looked at the superconducting qubit, when we looked at the topology of the qubit, this is hard coded. So that means this chip will only be able to perform certain universal gates, and so that boils down to the interpreter. I call it interpreter. Yeah, the compiler rather. To compile your code. You want to perform an X gate, you want to perform a CC NOS gate, to compile it down to this fundamental. They call it, is it local state? There's a term they call it on the IBM Qiskit uses to call the states, the gates that your qubit, your local device can carry out. The device cannot carry out all the gates at once. It cannot carry out all the gates, so only few gates. So your compiler needs to break down what the person is giving you to a form that will be digestible here. So this is what is happening here. This is your measurement. The items on red here is measuring it and giving out a feedback to whoever sent in a computation. I'll send all of these things. There are links where you could check some of these papers and some of these things out. So so those are the three I was looking at. Those are the three qubits. I tell you, I'll not mention all of them. I'll not mention all of them, but I did write some down. I think I wrote about quantum dots. Quantum dots. Quantum dots actually use, yeah, this is an example. This looks like quantum dots. Yeah, quantum dots, they actually use stable atoms. So you have an atom that is on its own, is stable. So we basically use rubium, the element rubium. So a rubium atom can be seen as a stable atom, and then they actually, basically by getting the tunneling, they use the tunneling between, the quantum tunneling between each of them. When you arrange them, when you organize them in this format now, there's a quantum tunneling that occurs between them. Of course, they are quantum particles. They use them to form gates that could be used for quantum computation. So this is actually a quantum dot. But I will not really speak so much about those quantum dots and neutral atoms. They are almost kind of similar. Okay, this is neutral atoms, not quantum dots rather. So neutral dots atoms, according to my right here. So, but basically, what I want to say is, so physical and logical qubit. We have said a lot about qubit design. I said the qubit is the fundamental part of what a quantum computer is. If you could get a qubit, you have gotten a quantum computer. So for a qubit, a quantum system inherently, it wants to dissipate energy. There's this the second law of thermodynamics, when we are starting to look at entropy. I saw a video about entropy. Entropy, there's a whole lot that we could learn from entropy. Nature on its own, everything wants to, so they want to seep out energy from themselves. So a qubit is nonetheless, a qubit left to itself will release energy, will also absorb energy from more energized particles. So qubits are very prone to noise. That's what I'm trying to say. And we are in an era of MISC, whereas we are saying noisy intermediate scale quantum computing devices. So what we have as of today, 2025, most of the qubits we have, most of the implementation, most of the quantum computers, they are still prone to noise. They are not even big enough, so they are intermediate. They are intermediate scale and they are noisy. Not only are they noisy, they are intermediate. So you see, there's a whole lot of room for improvement. Not only improvement on the software side, but improvement on the hardware to make these things less noisy. So they are noisy number one, and they are intermediate. We are talking about 400, 500 qubits. Whereas to properly model an atom, we should need probably, let's look at 10,000 to a million entangled qubits. Entangled qubits. That's a whole lot. That's a whole lot. So not that we are turning down the steam, no, we are still going full throttle ahead. This could be seen as the era of classical computation where we're having. I read a book, Cheap Wars. If you read Cheap Wars, you see how when they started building the semiconductor revolution we have, there was a time where transistors were very few. In fact, the first computer PC processor we had only a dozen processors, a dozen chips on it. And now we were able to, using lithography, advanced lithography techniques, EUV, we're able to reduce the size of transistors. We are still using transistors now. The only thing is that the transistors are very, very small. They are very, very small to the extent that it's coming up with another problem. They are even starting to have quantum properties themselves. The world we are living is sometimes when you're able to see a problem, you better be able to stand in a state to offer solutions. So the quantum system we have now, they are noisy, they are intermediate, they are not to scale. So we need to look for methodologies to make them more reliable. That's what I'm saying. So one of these methodologies, aside error correction, I will not look at error correction because that's beyond the scope of what I have here. But what I want to cover is physical and logical qubits. I learned this term quite recently. A computer or a how will I put it? A a company can come up and say we have 500 qubits, we have 1,000 qubits. I will not mention any companies now, but most of those qubits, they are just physical qubits. As we explained the superconducting qubits, we saw them. There were many. There were four. There were four qubits. But theoretically, if I want to perform a truly quantum operation, remember those qubits might have limitations in terms of number one, noise. A qubit has noise. And number two, based on the modality, you might not be able to implement the total Hilbert space. There are some complex states. There are some, how will I put it, imaginary states. Guys, I'm using imaginary numbers now, real number. They are real states, they are imaginary states. They are always imaginary components, just that with the scope of what we do, we mostly focus on, we are in the educational branch of things. We focus on the real, that's why you see, when you do harder math, you simply get the probability distribution is 1 over root 2. That is, if you get the probability, you're having a 1, is a whole number, is a rational number. But there are some states that are irrational. The probabilities are irrational. You're entering the imaginary domain, the complex domain. So a qubit might not, based on the implementation, might not be able to physically write all address, or you cannot map all of those things. So what happens is that a computer or a company might have 500 qubits on a chip, but when they want to start doing computation, they start shrinking them together. Maybe a group of qubits work as one. Like in this example, you see, they have grouped this bunch of qubits. They don't work independently. They work as one. It's a very, very crucial, it's a very, very crucial feature of the mixed era quantum designs we have. Most implementations are they are should I put it, they are grouped. And so when you group it into a single qubit, you have many qubits, you have 5 qubits, it might be 6, it depends on whatever you are doing, and you're able to group it to 1 qubit. That logical qubit now has the access to do almost all the, or should I call it all? A logical qubit is a qubit that has the access to represent all the possible states, to be more resistant to errors. So you might have 500 qubits. At the end of the day, you have 32 logical qubits. Do you understand? Someone might have 10,000 qubits, at the end he has 500 logical qubits. And I was listening to this recently. There was a show I was listening to. They were talking about the show was this year, and then they were talking about that we have left the era of stop looking at qubit count. Don't say this company has 10,000 qubits, 5,000 qubits. We should start looking at logical qubits. That we have left qubits number to logical. How many logical qubits can you boast of? So that's one thing we should do when designing qubits. We start focusing on logical qubits. Logical, I've explained logical to the essence that it is able to represent or to be in the entire. A logical qubit is simply the real qubit idealization. You know, when we are representing physical systems, like we say in an ideal system, in an ideal capacitor, in an ideal resistor, in an ideal inductor, a logical qubit is an ideal qubit. You can do all those possible states, whereas most qubits are limited in one way or the other. So that is what I'll put about that. So that is the end of basically the technicality that is involved here. Let me see what I have here to share. So these are some of the few. I like adding this to my presentations. These are some of the companies. There are more. There are more. In fact, it will shock you. Mercedes Benz. One time I was on X, Twitter, formerly Twitter, and then Mercedes Benz, they were advertising a role for a quantum, should I say, computing specialist. What would they use him and do? Obviously, when they want to start simulating, they don't need to build advanced physical systems, air tunnels, all of that. They try and represent them in quantum computer. Everybody wants to be ahead of the race. So these are a few companies that are actually actively being involved. Many companies that you'll be shocked to. In fact, if a company is not involved in quantum computing rather, you write them a proposal, shoot them, tell them, sir, do you know that quantum computers can do this, can do that? Then let's see what they will tell you. So quantum computing, studying it is not a waste. Just get to know your bearings, right? And seriously, you'll be able to work anywhere, especially in the area of mapping those things, because the problem spaces are very wide. You'll be the one to have to sit down, crack your head. Okay, this person wants to increase the number of cells or wants to increase the temperature tolerance of social molecule. It's now you that will sit down and map it to an available quantum computer. That's where the work comes in. So, with that being said, I would like to think I have a little bit time for questions, but thank you so much for being with me. This is some of my references that are available. So if you feel free, I'll try and share this later on so you could go through some of these. There are more. There are more. And that's all I have for you now. That's all I have for you now. Thank you so much. Please, if you have any question or anything I should further clarify, I'll be willing to do that. Or anything you want to add to what I've said. Thank you so much. And
Yeah,
God
good
bless
afternoon.
you.
Good afternoon.
Yes, sir.
How are you? Yes,
Yes, I can
I
hear
have
you.
a yes, I joined the meeting late, so maybe I missed out on your explanation on that part. So I heard you talking about classical computing. Yes, and what I want to know is the relationship between this classical computing field and quantum mechanics. Because when you go into studying quantum mechanics, there is the pattern in explaining. First start with classical mechanics, then you go to there are about four. But the last side is quantum theory, then we have quantum mechanics, quantum mechanics, then we have special relativity. It's all about we have this and practical to the quantum theory. We're talking about this tiny particles. And now, this one I'm talking about particles like the electrons, muons, ions, all of these kind of particles. I'm not actually talking about physics because now, let's I don't know the relationship between one of these two things we are saying and the particles that I'm talking about in this mechanical thing. If there's any kind of relationship between these two fluids, and whether one is actually how to study, how to properly study the other. Like one spoke about entanglement and good doctor. What I want to talk about those stuff. And also those stuff are also properties of quantum particles, not privy to just the quantum particles on their own. Yes, they are saying that quantum particles is big entanglement particles are all of that. So I mean very, very, very good at the moment. So what I'm just trying to know is religious similarity. Religious similarity between these two fields. Because I'm seeing them as two different fields. Like this one is about computer related stuff. Like we're showing chips and processors and all of that. But I'm not trying to see, okay, what relationship between it and this particle field, chemical particle field on its own, so that I can truly grasp the feel idea. And also, yes, towards the end of your presentation, you spoke about the effectiveness of this thing, like you said, method design for other people. That is for council, people that are good at council practices to go to simulate some certain things. So I was about to ask about that when you're very clearly right about it. So what I really want to know is the relationship, even about between those two things. Yes. Thank you.
You mean the relationship between classical and quantum computing? Is that what you mean, Mr. Kenneth?
No, no, the relationship between quantum network and quantum computing. Quantum network and quantum computing. If they are either of them,
Okay, now when you look at quantum mechanics, quantum mechanics is actually, how will I say, quantum mechanics was born. They call it the Solvay. Please, if I'm right, can someone just check the Solvay Convention of, I think that was 1933. 1933. So quantum mechanics on its own, it was introduced as a field because scientists, Einstein inclusive, Heisenberg, Niels Bohr, there were many of them. The Solvay conference, they discovered that classical mechanics could not actually explain everything that was observable about minute particles. There were a whole lot of postulates. There were a whole lot of debunkers. Some people were saying, "Oh, it's because of maybe we can't observe it better. It's because we have not been able to do this, do that." But basically, in the Soviet conference, they discovered quantum mechanics was true, and it has been tested and proven true. Something like the double slit experiment. There are very many experiments to prove that matter is actually in the subatomic level is actually quantized. And if you look at, I'll send you
the
the
double speak
paper.
of
I'll
fairness.
send you the
The double speak of
yeah.
fairness is
So
actually
I'll
to
send you.
show right way particle and behavior.
Yes,
Same motive.
yes. Okay, yeah. So basically, when we look at quantum computing, Richard Feynman in the year 19, I think that was in the 1960s, is what is considered one of the father of quantum computing. He said that I wonder how he was away ahead of his time because in that year, actually, computers were not as complex as what we have now. So computers they were very, if maybe you had ENIAC, all those UNIVAC, those computers, those giant calculators that could fill rooms. I'm sure our smartphone of today is more powerful than them. But he was able to see that in an ideal system, you will not be able to use quantum, classical means to to illustrate, to fully represent a quantum system. It's really deep. I'm reading a book currently. It's called The Universe in a Box. The Universe in a Box talks about simulations. So by the time you see people starting to simulate, they want to simulate the real world, not just simulate to show it on the screen, but to know how your interaction with the real world, your interaction with the microscopic world, will create a desired output. So part of that, what I call was covered in that book was quantum computing. Quantum computing is inevitable if nature if you want to simulate nature better and better, if you want to know how nitrogen reacts with nitrogen fixing bacteria to create ammonia on its own, all those subatomical processes, if you want to understand even chemistry better, if you want to understand black body radiation, there are some properties that if you want to do them, you need to use a quantum mechanical approach. Quantum mechanical approach. So basically, we now thought that, oh, this thing could be used in computation. I started with defining what computation is. You're trying to take measurement and then infer a solution, infer a feedback on the system. So basically, imagine now we want to model a coffee atom as they call it, or a water molecule, or whatever. The appropriate means will be to use a quantum system. And if you think of it if you think of it, if you want to think of it, you see that nature on its own is performing quantum computations, because when you mix two elements together, that's in chemistry now, or you allow two particles to interact, two photons, already inherent to them, they already have a feedback, they have an output. How do they have the output? They know if two photons interact, they know which one would come off with a higher energy level, which one will lose energy. They know how they will interfere, how they entangle. So nature on its own, as we speak, is performing a quantum computation, and we are seeing it all around us, the way sunlight is reaching us, everything. So what humans are trying to do is a form of a simulation to simulate what nature is doing on hardware, so that we could use it for our own means, so that we use it to better our production of certain materials. The world might look magical to you today. We have drugs, we have aeroplanes that fly, we have rockets. Everything might look perfect, but my brother, my sister, if you look deeply into the situation, you see that we have not scratched the surface. And it's because we don't really know any better. We have to manually do these things, compute. Maybe a scientist has to study for 35 years and then come up with a new molecule. But thank you, the fields of AI is creating a whole lot of breakthrough in that, in molecule design and molecule analysis, to come up with a new molecule that has a particular output. So a quantum computer, it will be useful for those kinds of intractable solutions. Please, someone has a question. Please, you could feel free to ask.
Well, thank you, Mr. Anekon, for your beautiful presentation. I'm quite happy because I'm coming close to what an engineer's thought is, in this field. So it's quite an interesting thing for me. Let me just give you a bit of my own background. I am a mathematician, forced to learn physics by virtue of research because of all this quantum language that is coming in. And therefore, I am forced to now see quantum computing as one field I can explore and get the best for myself. It's quite motivating. And I'm happy that you have come today from the angle you spoke, because we have had other speakers during this course of this program who have spoken from different research perspectives. So your own now combines almost all. Yeah. So I love you. Most of these books that you have mentioned that you have read, A Universe in Nature and all those other ones that seems to be, a lot of abstract books that have encouraged your thoughts. I think you should add it to your references so that you can also look at them. The other thing I want to comment about is on the last question that was asked. Yeah, I think the person asked about quantum mechanics and quantum computing. Yeah, the first thing I want us to see is that, quantum mechanics is 100 years. Now, I don't know how many years quantum computing is, but quantum mechanics came as an intuition. It was an abstraction because the scientists of that time were thinking in the abstract that if this can work this way, then the general laws do not hold. And from the physics perspective, the classical and the quantum came into play and all the directions were seen. So in essence, from the mathematical perspective, we look at a quantum object is an object that does not obey the classical laws. Classical in this sense is simple. Okay, when we say something is non-commutative, it means if I take a value A multiplied by B, 2 times 3 gives me 6, and now do the same thing by 3 times 2, and it doesn't give me the same result, then there's a problem. And this only happens when you deal with operators. Now, those operators in the concept that you have described them are, for example, elements of the Hilbert space that you have been mentioning. Okay, operators in Hilbert space are generally non-commutative, and then they obey some certain laws. Therefore, we cannot just take them like every other thing that happens. And this is the basic truth about how to start looking to the concept of quantum bits as the bits or the roots of what will be used in quantum computing or what is being used presently. So therefore, for somebody that wants to get a clearer view, you need to understand some bits of background of physics, possibly some mathematics, and then you get a clearer view, then you'll be able to move. You will observe that most of the things that are being measured here are in matrix form, and they are generally complex. Now, if you take a complex matrix, take any two complex matrices and multiply them, they won't give you the same result. So this is the beginning of what is non-commutative or what is called quantum. An example of an operator is a matrix. Now, generally, we know if we have two matrices, matrix A multiplying matrix B, we do not generally get a result of matrix B being multiplied with matrix A. So with this concept, we started in mathematics, and we have been following with physics, and now see where we are. There is a lot more to be achieved. My general comment will be that for all of us that we are working together in this field in Q Nigeria, I think we need to do more work together. And most of the researchers who are now out, like Victor, like Kenneth, and all of them that are in different institutes abroad, with the enriching knowledge they have, we should organize more of these interactive sessions that we give lectures in the different fields that we are, then we will all share new things. I will borrow from the engineer, borrow from the physicist, and I will now come clear. Then the engineer will now see, oh, okay, this theory you have brought us from math and physics, then I can use it in what I'm doing practically. This is the way the white people do. I think our interaction will beget a lot more good things to us if we can try to do it. Maybe every quarter, we just organize an online, like in Q Nigeria, we are always requested to give talks. So this kind of talk, you can make it a module that maybe every 3 months, whatever you have done in research, whatever you are up to, we give it a talk like this. Yeah, and if we do that in a year, I'm betting it with you, we will achieve so much because I have learned so much in the last 2 weeks. Yes, so this is my own thinking and this is my suggestion. I thank you so much for this talk, and I hope this organization is going to move higher than this. Thank you for the lecture. Thank you.
Thank you, everyone. Thank you, sir. Bye-bye.